And basically, just to give you a brief summary, I applied for a Google Summer of Code project, and my project was called py4science. The goal of it is to do symbolic analysis to derive equations of motion for mechanical systems primarily, and really have all the symbolic tools available to you, but also be able to generate code for numerical studies. So I kind of wanted a little bit of both, and I found the tools out there kind of lacking. There's a lot of tools out there that do certain things very well, but there's very few that have kind of all of it in one place. So my research is on bicycles and their dynamics and the control of them. And so for this, we use these models of bikes. We derive the equations of motion for them. We study their stability. We design controllers for them to analyze how they handle and see how they perform and see how design parameters affect the dynamics, essentially. It's a challenging system to model, and to date, no one's actually written down the equations of motion for even like a simplest, not the nonlinear equations of motion for the simplest bike model, which makes lots of simplifying assumptions. So it's somewhat challenging, and from a symbolic point of view, to get those equations right it's somewhat of an accomplishment. Lots of packages out there can do it numerically, and you can probably go into like Autodesk Inventor and grab a bunch of shapes and put them all together, and you can get this thing to behave the way it would, but you don't really have any control of the equations. You don't get to see them. You can't play with parameters in the same way you could if you had a function which defines the right-hand side of the ODEs, which is really what you want. And it's hard to verify that they're correct. So a lot of effort has been put forth to look at the bike and pick a set of parameters and compute the eigenvalues of that system and verify that, if you use Lagrange's method and he uses Newton-Euler, no matter what, the equations of motion are the same, and you should be able to get the same eigenvalues. So kind of validating models was a large part of the motivation I had. And I wanted to be able to extend the language I'm working in. So the current tools out there, commercial packages, don't really offer that much. There's a variety of them. Familiar with MATLAB, Mathematica. There's a lot of tools used in industry that, again, they're mostly focused on the numeric side of things and not really on the symbolic. And most of them aren't real complete programming languages. So I started making a little shopping list of things I'd like, and this is kind of what I came up with. I wanted to be able to do everything symbolically, and I wanted to have the ability to take those symbolic equations and then do numerical studies with them, and have nice, easy ways to do LaTeX or web interfacing, and publication quality graphics, and kind of work all in one place and create animations, all this stuff. So that was the motivation. And so after looking around, I saw that Python had a lot of really nice packages, SciPy, NumPy, IPython, all this stuff, Matplotlib for plotting, and no single other package I found, like the commercial ones, had all of these tools in one place. MATLAB has all the numerical stuff, symbolic stuff isn't so good, plotting is okay, animation's pretty poor. And the same goes with all the other ones. They had their strengths, but they didn't really have the whole thing. Python was really the only place that I found that you could do everything. And for code generation, the text processing stuff at Python makes it pretty neat and easy to just, once you do all your symbolic stuff, you can generate code. And so that was a big plus. So getting down to the structure of it, the focus of py4science is really on classical mechanics, so systems of rigid bodies and particles, and forces and torques that act on those particles and rigid bodies. They can be all nonlinear. You can use linear models if you want, but you don't have to. And what it does is essentially implements a tree of points and reference frames. So each node in the tree is either a point or a reference frame, and it's oriented or located relative to the other ones through a connection. So when you create new nodes, essentially new reference frames or new points, there's this connection between its parent and it may have children as well. So at the top of the tree you have...
I imagine the root node of that tree is assumed to be an inertial.
Exactly.
Okay.
Yep.
That
So,
assumption has to be made.
so yeah, again, this is the stuff I'm working on. This is standard, and for most systems that engineers use, unless they're dealing with really small scale, really large scale, classical mechanics does the job. So that was my focus.
But the others may not necessarily be inertial, right? You
Right.
Have rotating.
Oh, yeah.
Only the root node has to be inertial.
Yeah, so absolutely. So you start out, and I'll show this in an example, but essentially your root node is it's a point and a reference frame at the same time, or it's two kind of combined to each other, or connected to each other. And so that represents the inertial origin and the inertial reference frame. So the two core classes in PyDI are points and reference frames. And with that kind of structure, when you create new ones, you're always orienting reference frames relative to a parent or locating points relative to a parent. So by doing it in this way, you create this tree. And that's nice because it gives you the ability to express a vector in unit vectors mixed different frames, or locate a point relative to any other point in your tree. So you have this nice functionality where you can immediately find the location of points relative to one another, find the orientation of frames relative to one another, angular velocities of frames relative to one another. So by kind of working with this tree structure, you immediately have all this bookkeeping taken care of for you, which is really, it's not complicated, but to do it by hand or even to do it line by line in a piece of code, rotation matrices and taking derivatives in different frames, it can be very tedious and it can take a lot of your time, and it's error prone. So it's easy to make mistakes. Yeah, so it's easy to make lots of mistakes if you have to do this by hand. So AutoLev is the program I learned to do this in, and it was written by some people at Stanford, and it does this really well, but it's got one developer, it's all closed source, and they haven't had any new functionality added for over 5 years. And it's old and it's tired. So I've tried to convince him to, jump on the open source bandwagon and maybe on Python, but not at this point. Maybe soon. So each of these nodes in this tree, either points or reference frames, they have various attributes: position, velocity, acceleration. The way particles are represented is by assigning a mass to a point. So if you may have a point which has no mass, and that just may be a point for convenience of orienting or locating other points relative to it. But if you assign it a mass, then it's when you go to form the final equations of motion, it knows that, okay, I need to find the acceleration of this point because it's going to affect the equations of motion. And similarly, if there's a force applied at a point, similarly with reference frames, if there's an inertia assigned to it, then that's going to come into the dynamics if there's a torque applied to the reference frame. So basically, it takes care of all this bookkeeping for you. So as you create this tree, you assign locations, orientations, masses, inertias, forces, and torques, and it does all the bookkeeping for you. So you don't have to, and that's really 99% of the time when you make a mistake deriving the equations of motion, it's usually a bookkeeping error. You forgot to put the equal and opposite force on one point that the other point that's touching has, and then your equations aren't right. So
what you're talking about right now was PyDI?
Okay. Yeah, so this is all implemented in PyDI. And so again, the core structure of PyDI is this tree structure which basically does all the bookkeeping for points and reference frames for you. And it handles moving and accelerating points, moving and accelerating reference frames. The core classes are the reference frame class, the unit vector class, the vector class, point, dyad, and inertia. And just a few of the methods they support. Rotate is a method of the reference frame class. So when you start out with your Newtonian reference frame, you can create a new reference frame by rotating it relative to that one. And so you can specify a simple rotation, say about one axis by some angle, or you can specify body fixed 312 angles and specify what they are, or space fixed, and eventually I'd like to do quaternions and Rodriguez parameters and that sort of thing, but at this point I've not done that. The vectors and unit vectors support the dot and cross methods and the express methods. So say I have some vector with expressed in inertial coordinates, but I want to know what that vector is in some other reference frame. You can just express it in the vector. So it takes all the rotations into account and puts it into another reference frame. Locate is how you create new points. It's kind of the analogous method to rotate. So rotate is used to create new reference frames. Locate is used to create new points. And then time differentiation of vectors, you need to specify the frame in which you're differentiating. So that is one of the methods. And then a few of the functions, this is just a small list, is so generate function, coefficient matrix. The generate function is essentially what you're doing is as you're going through and you're analyzing your system, you come up with all these symbolic expressions for the kinematics and the dynamics, and then at the end of the day, you do your simplifications, you make them as nice and clean as possible, and then, okay, I want to be able to take these equations I've generated symbolically and create a Python function that I can use to execute and study it numerically, say. So generate function basically takes a list of SymPy equation objects. So what they are is it's a relational object which has a left-hand side and an equals and a right-hand side. So it takes a list of those, and spits out a Python function which lets you evaluate the right-hand sides and returns the left-hand sides. So for numeric stuff, it does that. It also, a lot of these equations will be linear in some terms, so you need to find the coefficients of the linear terms. So you give it a huge list of equations, and it'll return back a matrix of coefficients, which are the coefficients of the linear terms. These other two ones are somewhat minor, but a lot of times when you're doing symbolic stuff, you need to make symbolic substitutions. So, for example, there may be some expression that occurs repeatedly throughout a number of equations. And instead of having this long expression show up in every one of them 20 times and making them pretty unbearable to look at, you might want to replace it with a single symbol and keep that equation for that symbol definition in a list. And in the case of classical mechanics, this happens a lot. So you want to basically keep these dictionaries, which can be used for substitutions. So Python dictionaries. And SymPy supports a substitute method, which basically replaces a symbol with the, you pass it a dictionary, the key of the dictionary gets replaced with the value in the dictionary. So it's a nice...
In this case, are the keys the string form of the symbolic expression or the actual symbolic
The actual
symbolic object?
yeah.
Not just the string form.
Right, so the actual symbolic object. This is a classic example is whenever you have sine over cosine, you just want to replace it with tangent. There's one, like some things you'd like it to do automatically, but you don't want it always to do it, so that's one that you might want to make it do. So just a quick code snippet. I'll show this in the IPython or a Python script that will make it look a little more clear, but essentially what I'm doing here is I'm instantiating a reference frame n, and I'm assigning the string n to be its name, and then I'm calling the rotate method on line 2 of that reference frame to create a new reference frame. I'm going to call it A. It's going to be a simple rotation about the 3-axis by an angle of q1. So basically every reference frame object has a 1, 2, and 3 axis. You could call them x, y, z, so they start out with orthonormal basis vectors. And you can instantiate all your reference frames in this way, and then once you've done this, you immediately can do dot products, cross products, and you don't have to do all the rotation matrices. It just takes care of it for you. Same thing with express. You can express a unit vector, or for example, this could be a vector. I've shown unit vectors, but you could write a long, complicated expression which has SymPy symbols as scalar coefficients of the unit vectors. They could be mixed in different frames.
Can we go backward, please?
Sure. So dot product is scalar, and so it returns a SymPy expression. In this case, the cross product's a vector, and I'm pretty printing things so that the unit vector objects would be like this is getting represented as a bold symbol. So when you use the iSymPy interactive shell, it does some pretty printing, and it makes the unit vectors bold and the scalar coefficient regular.
So the bracket operation on a reference frame gives you
Yes,
a
exactly.
unit vector.
Yeah. So yeah, excellent point. That's
And the subscript there stand for the axes then?
this guy, like
No,
the
the subscript in the SymPy.
yeah, that's a unit vector, the third unit vector of the C frame. Say, is that what you mean?
Yeah, so does that correspond then
Mhm.
to axes
Mhm.
before?
Yep.
But then the axes between different reference frames here are different, are going to be different.
Mhm. Yeah. Yeah. But so essentially, yeah, I didn't make this clear. Each reference frame, when you instantiate it, has 3 unit vectors kind of fixed to it, and they're orthonormal. And you access those unit vectors by the index method of I think, what is it, get item?
Yeah.
The
Oh,
get
reference frame object.
Yes, the get item method of the reference frame object. By default, I use 1, 2, and 3 as the 3 indices for these unit vectors. So this operation here returns a unit vector object, which,
I have a question for
yeah.
you. I can see why you used 1, 2, and 3
Mhm.
because for mechanical things.
I want to make it 0, 1, 2. And
Zero-based indexing is very odd. I mean, in physics, I've never seen
Yeah.
a physics book written
Yeah.
in zero-based notation. On the other hand, in practice, you're going to end up using this in the middle of some big Python
Mhm.
code where you have other lists and other
Mhm.
NumPy arrays and whatnot.
I-
Aren't you going to go completely
Crazy.
bonkers
Yeah,
keeping track of that offset? The fact that these guys are
Mhm.
the only thing that is
Yeah.
one offset in your world.
Mm-hmm. Yep, and I'm going to change it. Actually, what I'd like to do is make it so you can specify the indices. So if you want to use XYZ, for an example, and that is more comfortable for you, you can do that. If you want to use 1, 2, 3, you can do that. If you want to use 0, 1, 2. So for the generalized coordinates, like these things, Q1, 2, 3, typically you'll see these things numbered from starting at 1, and same with the unit vectors, or you may just see X, Y, Z. But I agree, it's an issue, and I have to keep it straight in my head, and I think I need to pick something and make it the default that's going to be the best for the typical audience. But I think it'd be nice to make it so you can change it.
I'm actually not so sure. Well, changing it to XYZ or allowing them to be accessed by name,
Mhm.
that could be useful. But I tend to believe, I don't know, just from sort of long-term experience and having made mistakes of this kind,
Mhm.
that it's better to consistency
Mhm.
is in the long term
Worth it.
pays off over nice special cases.
Uh-huh.
Because the nice special cases are very attractive when you're looking at them in isolation. They're like,
Mhm.
oh, that makes total sense, and look at how clean the notation is, and look at how elegant I can do this thing right here. And
Uh-huh.
that looks like a super convincing argument when your head is thinking about that problem.
Mhm.
Then what happens is you take a step back and you go and think about something else for 3 months.
Right.
Someone else comes back. And then you return, and you've forgotten the justification and the rationality for that special case being
Mhm.
whatever it was.
Mhm.
And then all of a sudden, now what you have is a
Why is it
why
doing?
is this thing different again?
Yeah,
And
yeah.
why do I have to remember? Or worse, you don't notice it, and you
Mhm.
simply assume that it behaves like the rest of your tools.
Right.
You do something and it blows
It's
up,
wrong,
and you get
yeah.
nonsensical results, and you
Right.
can't understand why. If you're lucky, you try to index the damn thing with a 0.
Mhm.
If you're unlucky, you index them with 1 and 2,
Mhm.
thinking that
They're-
you're indexing the second and third, and instead you're indexing the first and second,
Right, right.
and the results are simply nonsense. They don't crash, but they're nonsense, and
Right,
you
right.
spend days debugging the whole
Yeah, yeah, yeah. That's
I mean, I think for better or worse, Python is a language whose ordered collections are 0 indexed, and
Mhm.
one should simply accept that that's a fact of life
Mhm.
and live with it.
yeah, yeah.
Rather than now, if you have an object where you can think of it as a non-ordered collection,
Mhm.
where the dictionary metaphor applies, then I think everything is fair game.
Mhm.
If it's an object that is very, very inherently not an ordered collection,
Mhm.
then I think it's okay to say, oh, I think of these things as an unordered collection, and then
Mhm.
my names are just labels, and it doesn't matter what they are.
Mhm.
But coordinate systems are not of that kind, because in particular in physics, there's a strong
Right-hand view.
notion of first, second, and third,
Right.
with typically third being the cross product of first and second. So
Mhm.
there's a natural order
Mhm.
in handedness, right?
Mhm.
A naturally ordered physics coordinate
Mhm.
system has a notion of 1, 2, 3 are those axes for which 3 is equal to 1 cross 2,
Right.
right? And that
Right.
defines a right-handed parallel coordinate
Mhm.
system. And
Mhm.
violating that assumption to describe them as an unordered object, I don't think is a good idea.
Yeah. You're not the first to mention this, and I will likely change it. I actually already changed. I was using index starting at 1 for generalized coordinates, and I've switched to 0. And I think I'll do the same for the unit vectors as well. And yeah, you're right. The more you work with it in detail, I completely agree. It's better to be consistent, and you may throw a few people off at first, but that's all right. They can suck it up and get used to zero-based indexing.
They'll
So-
thank you afterwards, actually.
Yeah. So those are just some examples of dot and cross, express. Again, these work, I'm showing examples of unit vectors, but they'll work on any general vector expression. So and a general vector expression in PyDI is one with SymPy expressions as the scalar coefficients of unit vectors. And they can be a mixed list of unit vectors, and it essentially stores it internally as a dictionary whose keys are the unit vectors and whose values are the SymPy expressions. So you can have a vector expression with 20 different reference frames involved if you want. But it just makes writing a vector through a complicated mechanism about as simple as you could hope for, because you can use all the convenient frames that describe the orientation of all the bodies you have to go through, and then some length parameter that moves in that direction, and then you're good.
I would do homework problems when I was taking my physics class. That would have been a lot more pleasant.
Right. Yeah, exactly. So this is an example of how you would use the locate method. So starting with the Newtonian reference frame, the dot O gives you, so N is I actually didn't show in the first slide, I haven't updated this. It should say Newtonian reference frame is the name I've given it. There is just a reference frame object, which is just reference frame. The only difference between a Newtonian reference frame and a regular reference frame object in PyDI is that the Newtonian reference frame also gets a point with it, and it also has a bunch of methods that are used for recursing the tree to compute the equations of motion. So once you've kind of set up your tree of points and reference frames, set all the forces, use this top node, or the root of the tree, to parse every child and calculate all the inertia forces, the inertia torques, and any active forces that are on the system. So that, just to be clear, this would be a Newtonian reference frame object. That would get you to the origin, which is a point object. And then locate is a method of the point class. And we're going to create a new point. And it's going to be located relative to the inertial origin NO by this vector, which is the second argument of the locate method. So it immediately computes position and velocity. Again, the velocities and angular velocities of all the points and reference frames are computed using time derivatives of the coordinates, which is what you need to do when you're first doing the kinematics of your problem. But eventually you're going to need to introduce, well, depending on how you do things, if you're doing Lagrangian dynamics, you might not. But if you're doing Keynes method or some of the other methods out there, you'll introduce what's called a generalized speed, and that's like a linear combination of your time derivatives of your generalized coordinates. And what it does is it kind of separates the kinematics of your problem from the dynamics of your problem, and it allows you to just immediately get first order equations of motion. So I think I've done enough talking, and I think it's best now to show you a little actual piece of code that would generate the equations of motion and see what they do and show some flashy stuff that'll maybe get people excited. Okay, so walking through this script, essentially I'll try to do it somewhat quick. I create this Newtonian reference frame. I declare some parameters. I declare some coordinates and their speeds. This returns two lists, one of the coordinates, one of the time derivatives of the coordinates. This returns the list of speeds and the time derivatives of those speeds. So for the rolling disk, if you're not familiar with this system, it's a classic non-holonomic system. It conserves energy. If you think about, I don't have any coins on me, but anyone have a penny or something? A disk in the plane would take 2 coordinates to locate it in the ground plane, and then 3 coordinates to orient it. So there's 5 generalized coordinates. But it has 2 non-holonomic constraints if you assume it doesn't slip. So it has...
I want to explain what holonomic constraints are for a
Sure.
non-mechanical.
Okay, so in mechanical systems, there's 2 main kind of constraints. One is holonomic, the other is non-holonomic. Example of a holonomic constraint would be like a 4-bar linkage. So it's basically saying that one of the coordinates is independent, and the fundamental constraint doesn't depend on the velocity. It's really dependent on the configuration. If you have a 4-bar linkage, and say there's a bar across here, if I specify this angle is determined, but it doesn't have anything to do with the velocity of this piece. It's really just fundamentally at the coordinate level. A non-holonomic constraint, on the other hand, it involves it's a motion constraint which essentially provides a relationship between the time derivatives of the coordinates. So pure rolling is a perfect example. That's a classic example of a non-holonomic constraint. What it's saying is that the velocity of the contact point in the ground plane is 0. So for no-slip rolling, it's a linear velocity constraint. So you can easily solve for the rates of travel in the ground plane as functions of the angular velocity time derivative coordinates. So that's, in a nutshell, the difference between. And it's non-integrable, so you can't take a non-holonomic constraint, integrate it, and express it only in coordinates. So that's the fundamental difference. So I unpack all these lists so that I can use them. And then I start with rotating or orienting my frames. And here's an example of the confusion. I'm using Q0 as my first one, but I'm using 312 as my, and it's, nowhere will you see in the mechanics literature body fixed 201 angles. And so I had to battle with this, and it's tough. But in any event, these first 2 rotate commands just create reference frames. They, by default, have no inertia. They have no applied torques. And then I create a reference frame which does have inertia. So a disk has, if you assume it's axially symmetric, it has 2 in-plane moments of inertia which are the same, and 1 polar moment of inertia out of the plane of the disk. So, and they also can be expressed in so the yaw frame of the disk gives you the heading, and then the lean frame gives you a leaned frame, and then the final frame that's spinning is the one that's ignorable due to the symmetry. So you can express this inertia in the leaned frame as opposed to the body fixed frame, and it ends up making things a little simpler. So once I've done this, I have the disk rigid body oriented. I've specified its inertia, and now I can locate the center of mass. Again, this guy here is the position from the inertial origin, which I'm going to take at this instant of time to be at the contact point. It's just a point that's fixed in inertial space. So at the moment I'm looking at this, the point of contact is in the ground plane is not moving. And it's located by the radius. This B3 vector is the one that points down into the ground in the lean plane. So minus r b3 gets me the center of the disk, and then I'm going to locate another point which I'm going to use for seeing how the motion of the disk is in the ground plane. This is some essentially I'm doing the kinematics right now. I need to determine the kinematic differential equations. What are those are the time derivatives of the coordinates specified as functions of the possibly the coordinates and the generalized speeds. So if I throw in a little print statement here, essentially we have the time derivative of that's the lean rate. The next one is the yaw rate. S1 is sine of the first angle. So I'm doing some pretty printing here to make things a little more compact. So instead of writing sine of Q1, I write S1. And essentially this is what you do when you want to define the kinematic differential equations. They're linear in the time derivatives of the coordinates, so I can take this matrix, invert it, generate a list of equations which represent all the kinematic equations. I'm not going to go through too much of this in detail. You need to spend some time to think about it in order to really absorb it. But once you've done the kinematics, you write the absolute velocities and absolute angular velocities of all your points and reference frame just using the generalized speeds. So in that example I showed you, I was able to, when I create a point, it immediately has a velocity. Where was it? Right here. So I locate a point, it has a position and a velocity, and we're using time derivatives of coordinates to express that velocity. When you go to the dynamics, once you've got your kinematic equations, you then introduce these things called generalized speeds, which are linear combinations of these types of quantities. And essentially what you need to do kind of to transition from that is go through all your reference frames and set the angular velocity in terms of these generalized speeds rather than these coordinates. And same thing with the points. So U0 is the first generalized speed, U1 is the second, U2. These are basically the angular velocity measure numbers in the B frame of the disk we're modeling. We set the angular velocity, the velocity of the point, and the absolute angular acceleration and the absolute acceleration of the center. And then we apply gravity. So this little nice command, you can see it's a method of the n object, which is a Newtonian reference frame object. And what it does is it goes through the whole tree, and for any point which has mass, it applies that mass of that point times the vector you give it, and that's the force. It'll add that to the list of forces that are acting on it. So if you've declared any other forces to be acting on a point, it'll just increment it by this mg in the n3 direction.
And you only have to specify it in this coordinate system, and then it'll do the right thing.
Exactly.
Whatever,
So
whatever reference frame each point was defined,
yeah.
it gets transformed.
So in this example, the only force that actually matters is the gravitational force. The contact forces do no work, so you don't actually need to. You notice that I didn't anywhere talk about the contact forces. So one advantage of Keynes' method is that for constraint forces which do no work, you just can ignore them in your analysis. Unless you want to know them, then you can introduce them and determine what they are, but they're not necessary to get the equations of motion. It's like Lagrange's method, but there's some differences. Anyway, so once you've kind of set your problem up, you run it and you call this form Keynes equations, and what it does is it goes through the tree and it goes through all the reference frames, looks to see if there's a torque or an inertia, and it will compute the active forces on that reference frame or inertia forces on that reference frame. So that's why it's important to have set the angular velocity and angular acceleration for each frame and for each point. And what it does when it does this, the inertia forces can always be grouped in two terms which are linear in the time derivatives of the generalized speeds, which you could also think of as the, like, say, x double dots. So mechanical systems are always like you have this mass matrix, which depends in general on the configuration, and then you have this q double dot plus some damping matrix, say, and this guy is actually going to be maybe dependent on time. So these are the gyroscopic terms, and it's going to be equal to all your forces. So when it goes through and forms Keynes' equations, it's intelligent about how it does it, and it builds the mass matrix by looking at the terms that are linear. In this case, I've written it as q double dots, but in Keynes notation, they'd be linear in the u dots. It also builds the gyroscopic terms, which are linear in things like ui times uj, or you might see a time derivative of a coordinate times one of the other generalized speeds. Essentially, these are gyroscopic and Coriolis terms, but they're always linear in those types of terms. So when it builds the inertia forces, it builds these things.
Most one-time derivative of those.
Yeah. So I mean, just from a unit point of view, these q's are things like angles or distances. So here we have radians per second squared or meters per second squared. And so the same thing, u is a meters per second squared or radians per second squared. So to get the same units, these guys have to be, they're always going to be meters per second squared or radians per second squared. And anyway, so it's going to build the inertia forces in this way, and it does it in an intelligent way and puts all the terms, it essentially builds them and puts all these terms onto the right-hand side. So in the end, you end up with a mass matrix on one side and then everything else on the other, which is nice because then all you have to do is invert the mass matrix and you have equations which can be directly integrated numerically, or sometimes, depending on the numerical integrator you're going to use, it'll have built-in functionality which allows you to just specify the mass matrix so you don't have to invert it, and it does the inversion for you. But all mechanical systems will end up with equations of this form.
Can I ask a question about the design? I'm kind of lost with the mechanical
Sure.
problems, but maybe about the software stuff.
Yeah.
So if I understand correctly, there's a node, in this case n, which is the root node of a tree. And that tree can be extremely complicated if you have many reference frames.
Mm-hmm.
And when you trigger something like form Keynes equations, that then propagates through the entire tree and does the calculation over each one of the nodes in that tree. And then so each node that you add, each leaf that you add to the tree, for example, it keeps some kind of copy of everything above it in the tree? You know, relations to everything above it?
Yeah, so when you instantiate a new node in the tree, it knows who its parent is. And when you instantiate it, its parent is told that it has a child. So there's essentially a list that's kept as an attribute of each of these nodes, which is the child list and the parent list. Well, so in a tree, you can only have one parent. So this structure only has, each node has one parent, but it can have multiple children. And so essentially that list is how all this bookkeeping is taken care of.
So if some intermediate level in the tree then changes, for example, does that then propagate down into everything else?
Right, so if I, say, called this command here, and then I did some other stuff, maybe added some reference frames, added some points, and then I called it again, it would use the current state of the tree. Does that answer your question?
Yes. on the other hand, when you do this, for example, on this really complicated system, and you're only interested, say, in the answer for some particular part of that system, then you've done all this calculation. Unnecessary calculation.
So in the examples, like in a mechanical system, I see what you're saying.
You can't avoid though.
You can't avoid it to some extent.
The equations are coupled enough that
Yeah.
you can't in general solve
One part separate from another.
in general
But if you have a tree structure and you want to know something about this part of the tree,
Mhm.
you're not interested in this part of the tree. For now, for example, you're not interested in some property of this part of the tree.
but
You don't, those are not coupled.
Well, in a mechanical system, they will be. Yeah.
The equations of motions are such that the actual, so you can't integrate, any question that you want to answer about this part of the tree is going to involve integrating the equations of motion for this guy. But the dynamical the coordinates and position for the coordinates and velocities for this guy are ultimately dependent on the coordinates and velocities for just about everything else in the linked system. So it's very rare that you'll find a system that decouples well enough into two completely isolated. I mean, it may exist, and it is in general actually an unsolved problem how to determine that. You know, to my knowledge, it's not a solved problem at least.
Yeah.
How to
So it's not a directed graph.
No.
It's a graph.
Well,
It's a graph in the object containment, yes, but the problem is that the equations of motion create couplings. Any path that can traverse, any node that can reach another node via traversal of the tree can exert dynamical influence on it.
yeah, exactly. It's essentially that.
So this is more of like a data structure for py than actual representation of, what's going on, because you can't isolate certain parts of the tree.
Yeah, I mean, in general, to get the equations of motion, you have to look at all of them. So one thing I do whenever I compute a dot product or a cross product, I add that to the list, and the list of things, dots and crosses that have been already computed. So in some sense, there's some intelligent computational savings that are happening because if it notices that I've already computed that dot or cross product, it won't recompute it. It just uses the answer it's already gotten. So to answer your question is, when I call this method, it goes through and computes what are known as generalized inertia forces. And those are things like m times acceleration, mass times acceleration, or Euler's equation for a rigid body. And if I wanted to add some other stuff and then call it again, it would be trivial to add a thing that says, if it already has this attribute and it's been set, then don't recompute it. So, but you'd have to be careful with that because maybe you change something that affects what the value of that is.
The converse of this question is if you add now things, you want to recompute everything, even if you've computed, you do this intelligent caching of previous computations.
Yeah.
You want to now cancel that. You want to, because of everything can, like you said, everything can
Yeah.
exert. I mean, not relations that are kind of static, not the rotations that you have of reference frames relative to each other. That won't change because you've added something in some part, but
Right.
some of the solutions to these.
Yeah, I mean, I guess it hasn't been on my mind so much because I typically think of, if I'm studying some system, I'm going to look at everything about it, make some assumptions, and then get the equations for that whole system. And then, okay, now I want to add this to the model, and I'll maybe add a few lines, but maybe make a separate file, and I'll call it something else. It'll be a different model. And yeah, so for the stuff I'm doing, the issue you brought up isn't too much of an issue.
Just to give you an example of a case that highlights how even things that appear independent in mechanical systems still have to solve the little problem. Consider two balls traveling in free space, right? And they're completely no forces, just free motion in space. They're traveling, their motions are completely uncorrelated and they're completely independent. So in principle, you could think, if I want to know where this ball is going to be at some point later in time, I can just integrate its straight path trajectory until that point in time, and I know where it is. The problem is that the one time they can interact is if they happen to touch each other. If they don't touch each other, their two trajectories are completely independent and you can answer questions for this one without this one. But if they happen to collide, then at the point of the collision, that'll change the trajectories for both of them, and we'll send them in. So you do have to integrate both of them in order to answer. And okay, that a case so trivial, obviously you could say, well, I could extrapolate and find whether they intersect. But in general, right, if there are complex interactions and things are bouncing, and you have, for example, balls in a confined geometry and they're bouncing, even though they appear not to interact, they may at some point in time cross paths. And so you can't simply say, well, there's no dynamical linkage between these two, I'm going to ignore this part of the system to find out what the rest is.
So you could do this interactively and kind of play with things as you go. I typically tend to create a script that I run and play with things, run it, and if certain parts of it take a long time, I'll maybe do some stuff interactively so I don't have to wait for that thing to go. But in the end, what you end up with this script is these kinematic differential equations. So I don't know, is that somewhat easy to see? Basically on the left-hand side, you have the time derivatives of the coordinates. On the right-hand side, you have things that are linear in the generalized speeds. So the speeds are the u's. C1 is cosine of Q1. And so essentially we have 5 differential equations which govern the motion of the 5 configuration coordinates or generalized coordinates. Keynes equations, though, there's only 3 degrees of freedom for this. So essentially what I get is this kind of, it's hard to read, but I end up with a list of first order equations that are essentially the u dots on the left-hand side, and then everything else, gyroscopic, Coriolis, and active force terms on the right-hand side. So you can see like mg times r sine 1. That's the gravitational force, and it's got some lever arm based on the lean angle, and then there's these other terms. So that's the result of calling Keynes equations, and then when I solve it, essentially I just invert the mass matrix and multiply it by the right-hand side. So what I end up with are these, the time derivatives of the u's and the time derivatives of the q's. And those you can integrate and then see a nice little animation. So that's like kind of the first thing to do. But then say you want to do some stability analysis, you can go through here, and I'm not going to go into the details, but essentially I linearize about the upright configuration, treat the spin rate as a parameter, and then I can compute the eigenvalues of that to see if it's stable or not. And then along the way, essentially the way I wanted pi die to be was you do the symbolic work and then you say, okay, I've got this symbolic expression that I'm confident it's right, and I want to use it, play with it, and do some numeric stuff on it. So this function called generate function is essentially this function I wrote for pi die, which it takes, you give it a name for the function you want to create, and you give it a list of equation objects. So these equation objects are pi die objects which have a left-hand side and a right-hand side. And it's a list of them. So in this case, it's the kinematic equations plus the dynamic differential equations. And then you give it function arguments. In this case, you need to specify the q's and the u's, and then it returns to you the time derivatives of the q's and the u's. And then any parameters, and then if you want to specify a docstring, you can. So I envision basically using pi die as a way to create a library of functions that are useful to some mechanical system you're studying. So you go through, you create all these symbolic expressions, and then you want to like output them into a file which you can then import these functions and do numerical study with. This little time equals true is just to get the right argument signature for the ODE integrators. Typically they want f of x comma t and then any optional parameters. Another function that I wrote for pi die was animate. So one of the things, once you do a numerical integration, you've got a time history of all the states, and this is what's needed in order to create an animation. And there's lots of, like Visual Python, for example, all of the objects in it, they need to have the center or some position on the object located in inertial space, and then 1 or 2 axes specified to specify the orientation. So essentially I created this animate function which takes as the first argument the frame in which to resolve all the vector quantities. So in this case, it's the n, the Newtonian frame. And then a list of tuples, a variable length list of tuples. And each tuple is a two-tuple. The first thing is a string, which is a name, which you could do whatever you want, but I use names that are kind of associated with the problem. So the CO is the center of the disk. I'm calling C the body. CO is the center of the disk. And then CO relative to N1. N1 was this other point in the ground plane. This rel method is just, it basically locates or returns the vector that points from N1 to CO. Or you can say it as the position of CO relative to N1, however you want to think of it. So it's a vector quantity, and what ends up happening is it gets dotted with the 1, 2, 3 vectors of n, and then you have three scalar quantities which represent the position in inertial space of the mass center of this disk. And then you do some similar things for these unit vectors which point out to the side of the disk, and then the two that are fixed in the disk and rotate with it. And then, some docstring stuff to just make it so these functions that are generated are, well documented. And in the end, when you do all this and run it, what it does is it creates this string. So this is the string that's created at the end of the day. And it's executable Python code. And it imports from future import division, import a few sine, cosine, tangent functions. And then it's got a function that defines the right-hand side of the equations of motion. And there's the doc string just thrown right in there, so it's nice. It unpacks all the function arguments, unpacks any parameters. The generate function command parses the list of equations and looks for trig terms so that you don't recompute all these things numerous times. So you're not calling cosine and sine and tangent more than once for any given time iteration or time step. And then essentially the list of equations that you gave it, which I don't know if you remember, was KD plus din diff, so kinematic differential equations and dynamic differential equations. Those all show up right here, and then they get returned. They get calculated and then returned. For the animation code, it's very similar. We unpack the function arguments. In this case, the only parameter that really matters is the radius of the disk. And then we return, this is the mass center location. This is the unit vector that points out of the plane of symmetry of the disk. So off to the right, and then the C1 and C3 ones are the ones in the plane rotating. There's some other ones that I generate mapping time derivatives of coordinates to speeds, eigenvalues. The rolling disk has a critical speed, which it's a bifurcation where the eigenvalues go from two real equal and opposite. So like a pendulum has two real eigenvalues, one positive, one negative. So in forward time, it's going to fall over, and backwards time, it's going to rise up. And for the rolling disk, it starts out that way, but at a certain speed, these two eigenvalues coalesce into a complex pair, and above that speed, you see qualitatively different behavior than below that speed. So finding what that critical speed was based on the parameters, we're a little function that generates that. Energy is another useful thing to look at, especially when you're doing numerical integration. You want to know that your conservative model actually conserves energy during the numerical integration. So if you form the kinetic and potential energy symbolically, then you output it, you should see that the total energy is constant, and you should see that the kinetic energy increases and the potential decreases, and you can feel confident that your simulation is well behaved. So this gets written to a file, and then you basically have a library of functions, which I'm putting in this file called rolling disk lib. I import it. I import some other stuff that allows me to integrate the equations and plot things. And let me just show you what happens when what we get here. So this is the little plot of the eigenvalues as a function of spin rate. You can see there's a positive and a negative eigenvalue. So those are the ones corresponding to it wanting to fall over. And then at a certain speed, they become complex and purely complex, actually. So there's no dissipation in the model, and which is interesting. The bicycle has no dissipation either in the simplest model, but you end up with eigenvalues which have negative real parts, so you get this asymptotic stability, whereas in the rolling disk you don't see that. So you can play with the initial conditions, and there's some interesting behavior. This is Visual Python that I'm using to animate it. You'll notice these lines in the plane are moving around. I think it has a limit to the amount of lines it can show on the screen. So if you use a small step size and you integrate for a long time, inevitably this line starts doing crazy things. And for some reason, they don't seem to have a way to remove points from that buffer. So you could have like whatever the maximum number of points that it can show. You can never, you'd like to just throw away the ones from the beginning of the simulation, but I can't seem to find a way to do that, which is unfortunate. But yeah, so you can, basically you have all this kind of functionality to study mechanical systems all in one place, and then use all the other Python tools out there to numerically integrate it, and do some stability analysis, plot it. I didn't show the energy plots. For some reason, why did that not plot? It should have... Okay, so this is the energy during numerical integration. So kinetic is blue, potential is green, and the total is constant, the red line. So you can see that it remains constant during numerical integration, which is comforting. So it's an example of use. So right now I'm working on the equations of motion for the bicycle, which is a more complicated system. The rolling disk is a non-holonomic system. It's got 5 configuration coordinates, 3 generalized speeds, and 3 degrees of freedom. But if you noticed, I didn't need to use, I can write the angular velocity and the velocity of the disk using only those 3 generalized speeds. I don't need to introduce other generalized speeds to be able to write down what those velocities and accelerations are. In the bicycle, that's not the case. You, in general, can't write down what the angular velocity and the velocity of every rigid body and the mass center, the velocity of the mass centers, without using all 6 generalized speeds. So in the end, you end up with a constraint matrix, which you have to deal with, and I'm close to getting PyDI to handle it, but it presents new challenges. So I think that's all I had for you guys. I've basically gone for an hour, and hopefully I haven't put anyone to sleep. Anyone have any questions? Oh, and let me show you. So there's a website for it. You can clone it at the Git repository. And I'd like to thank Andre. Andre is awesome. He's very available. He's a ninja in Python, and he's got cat-like reflexes, and he helped me a lot, and I learned a lot from him. And then my advisor and my lab mates, Thomas and Jason, all have provided a lot of valuable discussion for the development of PyDI. So, thank you. I have other examples I can show if anyone wants to see them.
I may be teaching some stuff at a physics department in a few months.
Uh-huh.
So if that happens, I'll be more than certain to
Yeah.
contact you. what extent maybe people here at the Redwood do more modeling than we do in other parts of neuroscience. But part of the reason why I thought this would be a very good presentation is because anyone who has a model that can actually be called a proper model, which fortunately in physics we do. That's not true in all fields. This is really sort of the way to treat those problems. Have a tool where you can manipulate the model at the symbolic level.
Right.
Keep it there.
Yeah.
And then from that representation generate numerical code for exploration, experimentation,
Right.
whatever.
Right.
And I did stuff like this in my undergrad, generating equations of motion in Maple, spitting C out in Maple, and hand coding the C.
Right.
Sort of hand coding C wrappers around stubs that would be generated by Maple, and it was possible and it worked well. It was a clunky, messy way to proceed, and it's kind of neat to see that now there are tools to do this in an integrated fashion.
Yeah, it was one of my hopes is that like for just like an entry-level dynamics class in undergrad, that they might be able to use this as a way to study some of their homework problems and just do vector analysis and vector kinematics, because the language of Python is such that it's not that much of a jump from the equations you see in your dynamics book to writing some code for it. And I was hoping PyDI could be designed in that way so that you don't have this, how do you make that leap from what I learned in a textbook and to programming it on a computer? And if you're working in C or even MATLAB, it can be pretty substantial to make that leap. And Python is nice for that reason. It's close to the language we speak in. So.
No, this is very cool.
Thanks.
Have you had to add significantly to SymPy as part of DiPy? So how much did you have to go back up into SymPy and either fix bugs or add features?
I added a few things. Like one thing, for example, was I was having to invert these symbolic matrices, and it turned out a lot of them were block diagonal, but there was nothing in SymPy that would take advantage of that structure. So Andre and I wrote basically a method that you pass a matrix to it and it searches it, and if it's block diagonal, it returns you all the blocks. And then you can invert those individually and then reassemble it. Yeah, so it's a lot faster. That was one thing. There's a few other little things, like one of the biggest issues I've noticed in pretty much every symbolic manipulator I've ever used. When I look at the equations of motion, I think of everything as symbols, but really some of them are constant and some of them are time varying. And in SymPy, those are treated as two different things. So, for example, if you have an expression which has all symbols, you can take the derivative of that expression with respect to any symbol, or the partial derivative with respect to any symbol. But if you want to take the partial derivative of it with respect to a function, say a generalized coordinate, which is implicitly dependent on time, we don't know what its closed form expression is, but we know it depends on time. You have to replace that symbol or that function with a symbol and then take the derivative with respect to that symbol and then back substitute. And this happens, I think, in Maple too, and maybe Mathematica. And it's a challenging thing. So if you want to declare things as time varying or not, things can get a little tricky. So another neat thing that SymPy has is this function called CSE. It's something sub-expressions. I think compute sub-expressions maybe is what it stands for. And essentially it takes a SymPy expression or a list of SymPy expressions and goes through and looks for anything that's being repeatedly calculated. And for anything that's calculated more than once, it introduces like an intermediate variable, and then it passes back to you a list of tuples which represent the left-hand side and the right-hand side, and then the expression or list of expressions which you originally gave it using all those variables that it introduces. So when you have these long, complicated things where there's a lot of repeated quantities, you can use this, and that's actually really nice because it makes things easier to look at, and then also from a computational point of view, if you're doing numerical stuff, there's a good chance that it's faster to do it that way if you have lots of memory available. So, but yeah, customizing the printing has also been really nice with SymPy. You can really change how it prints things, and so like PyDie changes how sign is printed, and it makes it easy to write code, output code, because you have these short expressions for things. Yeah. So definitely, it's pretty powerful, and it's a good mailing list. I don't know. There's good discussions on there. So.
What are some of the other systems that you've applied it to?
Let me show you. There's a double pendulum with damping at both joints. Let me see. You just commit anything. So hopefully this, right now I'm in the midst of a lot of changes, and so this is probably pretty hard to see, but essentially there's a very small first pendulum and very large second one. And so, Visual Python has a bunch of basic objects, spheres, cylinders, and for just getting an idea of how the system behaves, they're more than adequate. And so you can, this has like a linear viscous damping between the hinges, and so it eventually decays down to almost zero. What other ones? I did the rolling torus, which is similar to the very similar to the rolling disc, just a little bit different. And this is at half real time, so there's another example. Yeah, I mean, having the ability to just get a window where you can drag and zoom and look at something is pretty neat.
So can you very easily change the parameters? For
Mhm.
example, for the double
Yeah.
pendulum, can you make them same size?
Yeah, it's so right here is where I set them. If I make them both, say 1 or 1.1, that'll immediately get reflected in the animation. So it makes it quick to just change the parameters and then see what it does. We can add a bunch of damping. That's very little damping. Let's do something like this. So, and you can play with the mass, and I think I have the radius of the. Let's see.
So now if you added a layer of traits on top of that,
Mm-hmm.
you could do that, without having to edit that file in here.
Yeah, actually, so that's the next step, and I really want to take advantage of traits to start, just change those parameters, see it change in real time, or at the very least, just restart the integration, but all within.
Did you see a discussion that we have with Prabhu on the Sage notebook mailing list, or the Sage mailing list about that?
No.
So William somebody brought up a question about, William has a student doing undergraduate physics stuff,
Mm-hmm.
and so I suggested that they look at least at the Python,
Mm-hmm.
and someone mentioned traits, and I basically briefly recapped the conversation we had in the car the other night about because Prabhu wrote a version of Python using TBTK. It actually exists already.
Right.
But the problem is it's god-awful slow.
Yeah,
By
that's
god-awful, I mean like 2 orders of magnitude slower than Python. So it's basically unusable. And so I was hoping Prabhu would reply on the Sage list.
Mhm.
He did. So I wasn't sure if the problem really was traits, and it was sort of, it's kind of unsolvable.
Mm-hmm.
And Prabhu seems to think that it's not unsolvable.
Okay.
That it's a matter of there being too many event handlers firing when they shouldn't have to be,
Uh-huh.
but that with a little bit of work, that layer of traits on top of TBT of BTK could be made at least much more performant. He
Right.
did say that he would bet it would be like VPython, which is hand-coded OpenGL, but that it might come close in
Yeah.
performance. He said it wasn't hopeless.
That's cool. Yeah, it'd be nice. That was on the Sage mailing list?
On the Sage mailing list about last week.
Okay.
Yeah, just search for a thread that was like, the title was something like undergraduate physics problems. Or
Okay,
something.
okay.
And I posted and probably posted.
Okay. Yeah, one of the things I've noticed in most of the Visual Python examples is that they create this while loop that drives the animation, and they do the numerical integration in the while loop.
Yeah.
And I instead take a different approach. I do my own numerical integration outside the while loop, and then I create the whole trajectory of states, and then essentially I'm just passing, rendering. So hopefully, I mean, it wouldn't be too much slower. One other example, what was the other one? Oh, yeah. This is a classic one, just a single rigid body. So this is when there's an initial spin about the intermediate axis. So these are actually the dimensions of an iPhone. And if you take your iPhone and spin it this way, it's stable. This way, it's stable. But about the axis here, if you look carefully, it does this spin. And that's essentially, that is an unstable spin axis. So that was one little.
Cheaper than breaking your iPhone.
Yeah, exactly. So.
Thanks a lot, Luke.
Yeah,
Thanks
thank
for
you.
coming.
Yeah,
And I don't
absolutely.
know how much of a commute this is for you, but you're welcome anytime to show up. It's very informal. We have sometimes more people, sometimes less. Sometimes we have nice talks like yours. Sometimes it's more, well, we have a problem and let's just discuss it and see what happens. We're basically trying to build up as much as possible a community of people using these tools.
Cool,
for
yeah.
research and whatever it is that they do in all fields.
Yeah, so is Michael, he's coming? Is that, he's another guy.